Alright, so welcome to lecture number 7, and up until now we've covered the ISA, and we've taken MIPS as a reference example for our course, and we're gonna stick to that. But now we're gonna switch to the hardware implementation, and we've known. I mean, by now you all know that there's a more generic name for the ISA. So ISA is somewhat technical. But however, if someone is speaking generally, generally speaking about computer architecture, so computer architecture, now you know that they mean the ISA. And there's another name that has architecture in it, but it means something else, and it has a different prefix, and that prefix is micro. So whoever is talking about microarchitecture, well, they'll be talking about the implementation of the ISA, and we already kind of mentioned that in the earlier lectures of that particular course. All right, so in this lecture, in this online recap, whatever you call it, whatever you want to call it, but I mean, in that particular part of the course, we're gonna go ahead and cover something that we call a data path, and you kind of can guess from the name that it has data. So basically, it is the ones and zeros that constitute the data in a particular, architecture. And in the case of MIPS, maybe it's the 32-bit word data, or maybe 32-bit word instructions. It doesn't matter. All right, and it has path in it. So another term to describe a path in English, and I really liked one of your colleagues in the face-to-face lecture said that a path could be seen as a route as well. And for those French speakers between you, a path, c'est un chemin. Et donc du coup, it is the way for the data to go through. So data path is the things that you're gonna draw, and the ones and zeros are gonna travel through this particular route. Okay, donc right. So from now on, I'm gonna start talking about the implementation of an ISA that we covered in the very first part of that course. Where's my laser pointer? So this is how we're gonna find out that how the ISA is implemented, and we're gonna go ahead and check an implementation of the ISA that is fully functional. And then, because I'm assuming that everyone knows me by now, and there's something that I care about a lot, especially in the context of the CA course, is how to improve the performance of a computer. So we're gonna find out that maybe there are some techniques in order to be able not only to have a functional implementation, but also somehow optimized on more and more performance-wise advanced, and so it's faster, if I can put it that way. Right. So what's pipelining in English? What is a pipeline in English, and in what context do we hear about it? So again, some of your colleagues said that it's mainly in the gas and the oil domain. So yeah, definitely something. It is something where some fluid or anything potentially can be transported, or can flow in there. So we're gonna see in that part of the course, I mean the second part of this course, what is pipelining in the context of computer architecture. But let's stick to the first version. And I need to make sure, I'm assuming, and this is a correct assumption, that everyone is able to write, you know, of the top of their heads, the performance equation. You all know that by now, and this is one of the outcomes of the course that I need you to keep. Once you're done with the course, once you're done with GUC, and once you're gonna hit the professional life later on, because it could be used as an analogy for so many things and in so many domains. So this is one of the important things that I need you to carry on with you from now until the very I don't know when. All right. So what is the performance equation? And we said, I personally said that performance is related to wall clock time. So basically, if I want to study performance, all I care about, the most relevant and accurate metric or measure would be the measure of execution time. So wall clock, how much time does it take wall clock time wise? Get it? So on the on your regular clock, how much time would a benchmark program would take if I'm trying to execute it on computer A, and then I can go ahead and compare it uh, to the execution of that same particular benchmark program on computer B. So I'd be comparing apples with apples and not just apples with bananas or something like that. So basically I need the benchmark program, and I'm gonna go ahead compare the performance, so hence execution time of two different computers using the same program. All right, this is one way, and this is what we talked about and tackled in so much detail in that, in the earlier lectures of my course. And I've given you in a way or another in this course and in the OS course, there's another reliable performance metric, which is, I mean, if I want to put a definition to it, it would be, I'm going to define a time frame, and then I'm going to go ahead and check how many jobs are being done by the CPU in that defined time frame. So let me draw something here as long as I have time. So let's say that within 5 milliseconds, I'm going to go ahead and check how many jobs can my CPU, do within that time frame. And then again, I can compare it with different CPUs. So the thing here that I'm trying to make in a way or another, I call it throughput. So this is the metric that measures in a way or another. Again, it's relative to the time, of course, but I mean, I'm fixing the time and I'm studying how many jobs are being done using the CPU. One or multiple CPUs, doesn't really matter. So let's stick to the execution time equation related to the equation, and see what that really means. So execution time, we've seen that it has 3 parts: instructions per program, clock cycles, so how many instructions does my program have that I'm trying to execute on a particular architecture, and then I'm gonna see how many clock cycles will be taken by the instructions, and what is the length of a clock cycle. So I can clearly see here 3 parts. All right, so the first one, what I'm trying to, I want to break it down and try to find out if this particular part, each of the parts here, is it related to the hardware or the software of a computer? Fair enough, because after all, any computer out there is made of 2 gigantic parts, which is the software and the hardware. So let's see. So instructions per program, in any way would that be related to the hardware? So let's see, instructions are usually, part of a program. So a program is made out of instructions, and the instructions are what I can find in the dictionary of the instructions, so in the instruction set architecture, which is basically defines the operations and the possible things that I can do using a computer from a software point of view, right? So this it has the feeling of being purely software. Fair enough. So yeah, so this is an easy part. This is the easy part of the equation. Let's move on to that part and try to find out whether it's software or hardware related. So clock cycles per seconds. So the seconds, how many seconds will be a clock cycle will be made out of? So this has the feeling of the frequency of a computer, and the frequency of a computer is a hardware component. It's related to the clock that I physically implement in my computer and I follow. So this definitely, it's another easy part in that equation, which has the it has a feeling of hardware here, definitely. So this is software, definitely, and this is hardware, definitely. What about that one? That one is kind of I wouldn't say ambiguous, but it has a special feeling to it from my side. So what about it? So this, in a way or another, it has instruction in it, so it's kind of related to software. But then again, I'm trying to find out how many clock cycles are needed per instruction. So clock cycles per instruction, would that depend on purely on the software? Definitely not, because this has the feeling of the way I'm gonna implement my ISA. So basically, if I implemented in a way that it will take many clock cycles to execute an instruction, right? So the hardware implementation of it, this means that my execution time will be slower. And if I implement it in a way using different techniques that I'm gonna cover, I'm covering one of them in that part of this course, it feels like we can reduce the number of clock cycles needed to execute an instruction. So this, after all, feels like it's related to the hardware, and it is related to the hardware. So that part is definitely ISA, and those two are related to the hardware. This is a definitely hardware component, and this depends on the implementation, so on the microarchitecture of the ISA that I'm choosing. Again, in this course, I'm using MIPS as a nice example. Why not just higher frequencies? So what do I mean by that? So let's see. I'm assuming that I'm still fresh in the computer architecture domain, and it's back in early 90s, no, mid 90s, and I got hired by, I don't know, Microchip. No, let me put it. Oh, okay, Intel. So I'm hired by Intel, and I'm a team leader of, I don't know, a new architect. That would be something to be a fresh graduate and a team leader at the same time. Let's assume that. Let's imagine this scenario, and suddenly someone is telling me that the Japanese created a extremely high frequency clock. Oh, awesome! So all I have to do is go ahead and just put it, and each and every time someone creates a even higher frequency clock, I can go ahead and put it in my computer. Is that feasible? And take a second to think about it, and keep in mind what we covered in the earlier lectures of this course. So is it feasible, is it viable to go ahead and have a even faster, each and every time, even faster clock, and cross my fingers and hope that things will go faster? Well, theoretically, in a way or another, yes, right? However, when reality hits, and it really hits hard, we had a problem. We've noticed that we needed a paradigm shift, because we couldn't just like keep on overclocking. No, that's not the technical word. Keep on augmenting the frequency of our clocks. So the problem was the energy consumption and the power, and the heat, dissipation. So this is what we called the power wall problem, and we couldn't just go on forever, increasing the frequency of our clocks. So yeah, and this is what I think I've mentioned for those who are attending my lecture, my face-to-face lecture, that we tried to cook pizza in a using a CPU, and I found this on the internet, which is extremely interesting. And you can notice that you can actually cook a piece of meat on a microprocessor. So, and this is real, it's not made up. So yeah, this is not the solution, and maybe there are, the different techniques that were proposed, it's because of that power wall problem. All right, so we're gonna start step by step. We're gonna cover the functional, I'm gonna call it this way, the simple implementation, which is functional. It works perfectly. So if you're gonna go ahead and use your VHDL skills that you acquired, that I'm hoping that you acquired in your DSD course, so you can actually implement it on the hardware, and it will work as a full computer. However, you're gonna notice, if you're gonna try and execute programs on it, it will be a little bit slow. All right, so yeah, let's go for it. Let's go for the basic MIPS as an example again, implementation. So I'm gonna divide instructions into three types. So I'm gonna start with the first type, and this type is concerned with loads. I mean, the first type has includes the loads and the store instructions, and those types of instructions are concerned with what exactly. So these are the instructions that are concerned with memory. So these are in MIPS, in the context of MIPS. So the MIPS ISA, these are the two only possible instructions that are able to communicate or to reference the memory. In the case of MIPS, maybe there's an architecture, there's an ISA out there that will allow you to, I don't know, to have some arithmetic operation that deals directly with operands from the memory and back to the memory. This is not the case of MIPS. The MIPS designer decided to do it in a different way. Right, so what about those here? Add, subtract, and, or, etc. So these instructions, they have the feeling of being mathematical and logical. So these are the ALU instructions, all right? Arithmetical or arithmetic and logical instructions. So these, we've talked plenty about those two in the first part of my my course. Still missing an interesting type of instruction here. So what would that be? So the memory ones, the ALU ones, and the ALU ones are usually R-type. Doesn't really matter for now. But I mean, there's something still missing. All right, so to give you a hint, so normally execution of a program will happen sequentially, and if I want to alter based on some conditions, those would be the branch and jump instructions. All right. So keep those in mind. We're gonna use them all the way in today's lecture. Fair enough. Three different types, and we're gonna see. Remember, the purpose, the objective of today's lecture is to create a data path that is generic enough to include every type of instruction that I'm stating here. Fair enough. So everything, single thing that I need to, propagate within my different hardware components or between my different hardware components, well, they should be able to implement and make it possible for those words, for those instructions to execute. So let's do that. So first thing first, in every architecture and every computer out there, there's some kind of execution steps that are present. So they are there in a way or another. So these are the basic ones, and then you can have more steps. But again, these are the basic steps. So whenever I'm going to execute an instruction, there are a couple of things that are considered. First off, naturally, in the context of the stored program paradigm. So since some time now, we're not feeding in real time or externally the instructions to a computer to be able to execute while we're programming and saving it somewhere. So we're storing it, and then we're gonna go ahead and read it from that particular place. We can load it. I mean, those who are taking OS, we can load it to the primary memory, and then we can partially and start reading it, etc. However, it is stored. I'm not feeding it in real time through an input, for instance. It's not my job. So this is the stored program paradigm. So basically what I'm doing here, the PC, so this is some kind of pointer. So the register that has the address of the next instruction to execute, or the current instruction, it really depends on the implementation. In the case of MIPS, it's the next instruction. So I'm pointing to the next instruction I want to execute, and yeah. So the next instruction I want to execute is stored in the instruction memory, whether it's physically independent from the data one or logically independent, doesn't really matter. It depends on the class of architecture that I'm using. And then once I have it, well, I'm gonna go ahead and try understand what kind of directive the instruction is asking the computer to do, and then we're gonna go ahead and execute it. Fair enough? So in a way or another, it feels like I need to get the instruction, understand it, and then execute it. So these are the famous fetch, decode, and execute, and they are present in every computer out there, and most computers out there, let me put it that way. We never know, maybe there's an exception. Could we have more steps? Yes, definitely, and we're gonna see in the case of MIPS there's an additional step. Here we feel like something's still missing, knowing MIPS, right? We've seen almost everything. We're seeing the ALU instruction memory, maybe there's the data memory that is missing, and maybe we can, read from it or write to it. Let's move on. All right, so here with the face-to-face people, we played a game, and the game was with the implementation abstract. So we're seeing the big picture of the different components that should be present in every computer. I'm not saying the IOs for sure, but I mean, this is what I care about for now. And these are the three types of instructions that I talked about earlier in today's lecture, right? So the memory ones, the jump and branch. I'm gonna stick to the branch for now, and then you're gonna cover the jump in the tutorial, I think. And then you're gonna see the ALU instructions. So the game here that I'm trying to play, go ahead and pause the video and create it. I'm gonna try and draw and play it. I'm gonna go ahead and draw arrows, right, to see what are the different components that are concerned with a particular instruction, and where does my arrow stop, right? And in what direction does it go? Is it only that way, or can it, have a U-turn or something like that? So this is the game that I'm playing. So go ahead, pause the video, and draw arrows in different colors for each of the instruction types that I talked about. All right, so I'm assuming that you paused the video and now you're trying to verify your answer. So let's start with number 1. So for ALU instructions, do I need the PC, the program counter? Naturally, for any type of instruction, I need the pointer to tell me, well, what is the instruction that I'm execute. So definitely the PC is needed for the ALU instructions, because it will be pointing to the actual instruction that happens to be in the ALU instruction. So this is definitely needed. What about the instruction memory? So the PC is pointing to somewhere, it has the address or something somewhere, so it's, indirectly pointing to somewhere. So it's pointing to the instruction that is in the instruction memory. So yeah, for the ALU instructions, I need the PC, both the PC and the instruction memory. All right, do I need the registers for my ALUs? So ALU instructions are usually R-type in the context of MIPS, so I need to have a source register, at least one source register, and the destination register, maybe 2 source registers in case of, purely R-type. So yeah, definitely I need the registers here. Fair enough. So I'm going through all the way to here till now with ALU. So are ALU instructions needing, would they need in any way the ALU? Well, it's in the name. So basically, yeah, definitely they need the ALU. Right? So we have all the way till here till now. What about the data memory? Do ALU instructions need the memory? Nope. ALU instructions are only concerned with the registers, and the result is stored in the destination register, so I will not reach the data memory with arithmetic logical instructions. So the arrow that I would draw would be all the way to the ALU. Would it stop here? Is that the end of it? Well, no, because I'm storing back in the destination register, so I'll have a small U-turn here and stop at the registers. So let's see it. So here it feels like we're going from the PC, all the way to the ALU and back to the register. And this is typically what I would ask in my exams. So something abstract, something basic, and you need to go ahead and try to understand the logic behind it. Fair enough? Go ahead and do it for the load and store, and you're going to find out that the loads and store, well, for the loads, because load and store deal with the memory, so we're going to go ahead and need PC, instruction memory. Definitely, I'm going to use the data memory for sure. Do I need the registers and the ALU? Well, remember, in loads and stores, well, I need to specify the base and the address. So the base is usually found in a register, so yeah, I will need registers for sure. Right? Will I need the ALU? Would I need the ALU for the load and store instructions? Well, base and offset, so I need to add the offset to the base, so there's some adding, and the adding happens in the ALU, or at least in a component, that should be in the ALU, which is the adder, right? So I'll definitely need to use the ALU. Now I could stop here all the way to the data memory, because if I'm storing something to the data, or if I'm loading something, well, I'm gonna go and get it from here and put it somewhere. Where am I going to put it? Well, in the destination register. So I could go back to the registers with a load instruction, for instance. So that would make it either stop here for store, or have a U-turn here to go back to the registers. What about the branch? So the branch based on a condition would alter the sequential execution. So I'll definitely need the PC, I'll definitely need the instruction memory. Branch unequal, for instance, I'm going to compare the content of two registers, so I'll need that. Comparing the content of two registers means that I'm going to do some mathematical thingy here, so I'm going to need it. Do I need the data memory? Apparently not. So what would I need? I'm going to go from here, and the result of that, whether the branch is happening or not happening, well, if it's happening, I need to alter the next address that is inside of my PC. So I need to circle back all the way back to my PC. We good? Next. Alright, so fetching and incrementing PC. How does the fetching happen? Well, in MIPS, well, it's happening sequentially, right? So I need to have the word, the instruction word that I have here, and then I need to move to the very next instruction. So the very next instruction is one word away from the current instruction that I'm executing. However, in MIPS, well, we don't use word addressing. In some other architectures, we might, but not in MIPS. So what should we do here? So here in MIPS, we're using byte addressing, so we'll have something like that. I'm gonna go ahead and check the address of the instruction of the next instruction I'm executing, right? And then for the current instruction, and then for the next instruction, all I need to do is add. It's one instruction away from the current one, so all I need to do is add 4 bytes, because with byte addressing in the case of MIPS, well, every instruction is 4 bytes away from the current one. So the next instruction is 4 bytes away from the current one. This is where I need to add 4 to the current instruction that I have, and hence I will have the address of the next instruction. So is this concerned with branching? Am I seeing branching here in any way? Nope. So this is the normal sequential execution. So each and every time I read an instruction, the next one that will be loaded, it will be 4 bytes away. So it will be the very next instruction. Fair enough? Normal sequential execution. Alright, now I'm gonna move on to the R format ALU operations, and I'm being a little bit specific here. R format in the sense of it's not including right now the I format. So all I care is register, and back to the register. Fair enough. So this is the where is it? Where's my pointer? Why do I keep on losing it? So this is the abstract format of it, and we're gonna find out that this is the more detailed version of it. By the way, I really like to call the registers a register file. So from now on, I personally, and it's out there in the literature as well, you're gonna find something that we call a register file, and the register file you're gonna find in there the defined registers that are usable as defined in the ISA. Right, so in the case of MIPS, in the register file, you will find 32 registers, and in which you're gonna find, for instance, the register 0 that is hardwired, etc., etc. Fair enough. All right. So here, what I'm trying to find out, and I go ahead and pause the video again. I'm trying to find out in the buses here and the arrows here. Well, how many bits do I have? All right. So here, it is the address of the first source register, the address, and in case of MIPS we have 32 registers, so the address should cover those. So address of the first source register, second source register, and the destination register as well. And then the actual word that I'm, data word that I'm writing back to the destination register that I will be choosing using this address, and the two source registers that I'll be reading through those addresses. So here addresses, and here the actual data that I'm gonna be using. And by the way, where does the in the case of R format ALU operations, where do those two read data go? Well, naturally they're gonna go to the, where is it, to the ALU. To the ALU. Fair enough. So this would be the first operand of the ALU and the second operand, and then we're gonna see what would happen. So yeah, how to pick up in the case of MIPS, how to choose one of the one source register out of the 32 available ones. Well, I need 5 bits, so it's true for any register address that I need here. So I dispose of 5 bits to the power of 5, which makes sense, right? What about the data? So what is the size of the word MIPS? So it is the 32. Fair enough. So these two, they go to the ALU. Awesome. There's something missing here in that figure. What would that be? Something interesting. So ALU, R format, I'm choosing the source registers, 2 of them, and I'm choosing the destination register. And here I can see that I've read the 2 source registers. I've used them in the ALU. What should I do next? Well, the result should go back to the register file. So basically, the connection that is missing here is from the ALU result all the way back to whatever I'm writing to the right data here, right? So the right data that I'm gonna go ahead and store in the register that I've chosen as a destination register. Well, I need you to notice something else here, the 0 here, and some of your friends, I mean colleagues, I don't know if they're friends, your colleagues, they said that this is a flag. What would that flag be? So sometimes in some architectures, and MIPS as well, so if the result of an operation happening in the ALU is equal to 0, well, I'm going to set the flag to 1. I'm going to raise the flag, say that the result is 0. Why would that be interesting? Well, it could be interesting because if I wanted to do some comparison, or I needed to know the result and act on it fast, maybe all I have to do is, while I'm here, to look at the flag instead of go ahead and read whatever has been written here, right? So for the time being, we're going to cover that in more detail later. For the time being, if imagine that I'm comparing 2 variables, like let's say A and B, so the content of, let's say, register A and register B, whatever those registers are. So if they're equal, and how would I know that? What is the easiest operation to know if 2 variables are equal? Well, the easiest way to do it, and hardware wise this is how it's done, all I have to do is subtract B from A. So if A minus B is equal to 0, this means that A is equal to B, right? So A minus B equal to 0, instead of going and writing back 0 here and using another instruction to see, well, if it's 0 or not 0, in order to know, to know what to do next, all I have to do is go ahead and read the flag. Well, if they're 0, if they're equal to 0, so this means that A is equal to B. So maybe I can use that in order to go faster, and it is the case. Awesome. Let's see the memory now. So this is the abstract version of it, and let's see what happens really. So data memory, awesome. I said I needed those as well. So all I need here is to specify the address from which I'm reading or I'm writing to. In case of something, an instruction that will write data to the data memory, well, this is where I'm going to feed it. So what instruction writes data to memory? A store. And in case of a data read, well, I'm going to read it from here, and that would be a load. Let me think about it for a second. Let's focus on the load. So here, as an example, so load will specify the base and the destination address. Fair enough. These are those registers. However, well, I need to specify the offset, and apparently I'm using 16 bits as an offset here. So hold on. I'm creating a data path that is compatible and being generic enough to include each and every type of instruction that I talked about earlier, right? Including the loads and stores. And up until now, we've seen, for instance, if I'm feeding something to the ALU, because I need the ALU, remember in R-type, for instance, I'm feeding it 32. And in the case of a load word, well, I need to read something, the base in a register, and then I'm gonna add the offset to it. And then again, if I'm doing that, this means that I'm feeding the ALU the 32 bits of the base. However, here the offset is not 32, it's 16. So that means that my implementation is not generic anymore, because I'll need a special path for the 16. Well, no. I'm gonna try and deal with it in a different way. Well, instead of just having 16, I'm gonna go ahead and add an adapter. All right, you can see it that way, that will extend my 16-bit field here to make it 32, so it will stay compatible with the actual data path that I started creating with the R type, for instance. Fair enough? So for now, you can see the sign extend as an adapter that will make sure that even if I'm using something that has, a bus, not a bus, a narrow for now, let's call it that way, that is less than 32, well, I'm making sure that it becomes 32 so I can continue. So it would be compatible. Now the technical question here is how would I do that? How would I go ahead and extend 16 to make it happen to 32, knowing that an offset to stay generic could either be positive or negative? So yeah, so how would I extend that? Let's send the name. Usually the most significant bit will reflect the sign. So all I have to do is go ahead and copy paste 16 times the most significant bit. Fair enough? I think you're gonna cover it as well in the tutorial. Alright, so yeah, so check this out. This is a big picture of the data path for now, taking into consideration the R format plus the loads and stores. Let's have a quick check on it. So basically the instruction that I'm getting when I'm decoding, well, I'm gonna go ahead and read registers, two source registers for the R format and the destination register, so I'll have that one. And then here I have two possibilities. Two possibilities. It's either I'm reading the second source register in a case of an R format instruction, and if it's not the case, if I'm doing a load and store, well, the ALU should be fed from somewhere else, and that somewhere else is nothing but the 32 bits that were extended from the 16-bit offset that I'm reading from the instruction. Fair enough? All I have to do is toggle something in the mux here, and according to your colleagues in the face-to-face lectures, you've already seen what a mux is and how to use it. Fair enough? So something will control it, and we'll know whether we're gonna go this way, we're gonna use this source or that source. So in case of an R format, I'll be using that source. In case of a load and store, I'll be using that source. And you can notice that this particular arrow is 32 bits, right? Because the ALU is expecting two inputs of 32 bits. This one for sure is 32 bits because I'm reading it from source register. And that one for now is 32 because I've just extended it from before, from the slide before. Fair enough? And then the result that's happening here, in case of an R format, well, you're gonna see that I'm not going to go through the data memory. So R format I will come here and I go back to the destination register that I need to write to. And in case of a memory instruction, well, I'm gonna use the red data that I'm storing, that I'm loading and storing back to the destination register. In case of a store, well, I won't even be reading data from the thingy, so it's already covered naturally. Right? So here again, I'm using a mux to choose whether it's a direct result of the ALU in case of an R format, or I'm going to use whatever I'm loading from the memory to put it back in the destination register. Right? Here you can notice something in blue, and we're going to talk about those later. Alright, so the third type of instruction that the third and final type of instruction that I still haven't covered in today's lecture, where it's the branch instructions, right? So it concerns the PC, and we said that in order to be able to know whether to branch or not, we need to have some comparison. So for instance, if I'm doing a branch on equal, well, I'm comparing the content of two registers. So I'm going to use the register file, and if I'm comparing, if variable A is equal, content of register A is equal to the content of register B, well, the easiest and fastest way to do is a subtraction, for instance. Right, so I'm going to use the ALU. So this is how it goes. Right, so I'm reading the two registers that I want to compare pair, and then I have again an offset here, and the offset, of course, this means that this is the target that I'll jump to. So because of it's a 16-bit, so I need to go throughout the through the sign extent. It's the same thing as before to stay compatible in a way. However, I need you to see. All right, so right, so I'm doing that, and if I'm jumping, in the case of the two being equal, right? So this is where I said I'm going to use the 0 flag here because it will be faster. Get it? So the branch will know that they are equal. So go ahead and rapidly jump to your branch to your target. So this is the ALU part of it. But then again, I need to go to the target. So how would I calculate the target? Well, I'll definitely need the offset that I'm getting from here for sure. And I need the actual natural sequential address of the next instruction. So basically it would be the normal PC plus 4 that I would have had naturally if I kept on the sequential execution. So if the branch is happening, well, I need to add whatever I had before, add to it the offset, the branch target, and then the sum of those will give me the branch target. And if the branch is not happening, well, all I have to do is ignore that, and I still have my very next instruction, which is PC plus 4 from before, as we've seen before. There's something that you need to notice here. I still haven't talked about it right now. What is that? Here. Why do I'm shifting by 2? So first off, shifting by 2 means, what am I doing? So I'm shifting left by 2, by the way. So what does it mean? It means that I'm multiplying by 4. Why would I do that? Think about it for a second. Now, the offset here, if you go ahead and check and make sure that I'm not saying stupid stuff, if you check the ISA, the offset is in words and it's not in bytes. So the branch target, it will be X words away, or X instructions away from the actual very next sequential instruction. And because in MIPS we use byte addressing, so in order to get the next instruction, well, all we have to do is go 4 bytes from there. But you can see that with byte addressing, in the context of trying to reach instructions, right, it will limit you a little bit. It will limit the distance that you can reach. So let me write it. I mean, I'm going to give you the logic behind it, and I think you also have a what do you call it? A tutorial on that, or a practice assignment on it. So this is the first instruction, second instruction, third instruction, fourth, etc., etc. So normally PC plus 4 will get you to the very next instruction. But imagine that in case of a branch, you're going to go ahead and reach somewhere, right? So with 16 bits, if I'm using byte addressing, well, you can see that you're limited. The distance is limited because each 4 bytes will be only one instruction away. But what if I wanted to reach even further? So I want to branch to something that is far, not that near. So what would be the solution? Well, the solution would be, instead of dealing with bytes, well, the offset will specify the words, right? So I will be X words. I'm going to branch to X words from the very next instruction. And because we're using byte addressing, a word is 4 bytes away. So all I have to do is every one in a branch, so everything that is one step away from the previous one is actually 4 bytes away. So instead of doing bytes, now I move to words thanks to that. Alright. Well, if you still don't get it, well, you're gonna get it because you're gonna practice it in the tutorial. Alright, so this is the big picture and the final picture of everything that we covered in today's lecture. So branch, and the only thing that is still missing is jump, and again, you're gonna see it in the tutorial. It will be easier for you since you've learned a lot of stuff today. Right, so every single possibility with every data path, all we have to do is toggle, toggle, toggle. See, even here we can toggle between the normal sequential execution, or in case of a branch, we're gonna use that one. So we turn it off and or on this max. I mean, we can toggle it to 0 or 1, so we can know what would be the next value of PC. Is it the normal one or the one that is resulting from a branch, the branch destination that is supposed to happen. And same is here for whether it's coming from the load, the instruction in memory instruction or a normal R type instruction. Fair enough. Yeah, go ahead and pause the video and try to figure out everything and verify that everything is covered here. Everything but the jump that you're gonna cover later in the tutorial. Alright, what I'm gonna cover next in today's lecture is how to deal with that. So you can notice that in order to decide which input to take into consideration, well, we have some control signals here. We're gonna cover those later. I'm gonna focus on that today and see what happened. First thing I need you to notice, and this is a typical final exam question, any type of exam question, my type of exam question. Imagine that I'm giving you that for the very first time, something that you've never seen before. Yeah. And my very first question is, using the information that you have on this figure, how many possible, what is it most likely the possible operations that could happen inside of the ALU. So if this is a control signal and the control signal is made out of 4 bits, so basically this means that I can select anything between a possible 2 to the power of 4 operations inside of my ALU. So theoretically, using the information that I have here, well, I have up to I have a 2 to the power of 4 possible operations here, so 16. And this is what we need to know by now, and we're gonna see that if it's true or not true in the next slide. Fair enough. So this is given now. I'm giving you that in MIPS. We're going to have only those operations. So we have 6 operations. This is why I need what needs to be implemented inside of the ALU. So I have 6. So 6, how many bits would be needed for 6? So basically I could have done it with 3 bits. But then again, I have an extra bit maybe for another, I don't know, to improve or to add new operations later or something like that for future use. Right? So at least we need 3 bits, so we're good with 4 bits. Now, another typical exam question of mine. Here, with 4 bits, we could have up to 16, so we still have 10 possible here. For some reason, 5 years from now, someone said that I need 17. So 17 operations of my ALU. Well, what should I change in order to be able to have 17 operations? Well, here, all I have to do is add an extra bit. Alright, so let's see what the MIPS people decided to encode the different operations. So let's see. For an AND, they decided, so it's a bunch of 4 zeros. See? So the control signal will be 4 zeros. What about the add? So the add, it's 0, 0, 1, 0. Fair enough. And here it is, they have their reasons of why they've chosen those particular values. It could have been any value. It doesn't really matter. What I want you to see here, and the last thing, and it's good to know. So we've talked about the Z flag of the ALU, and this means that I'm going to deal with it whether the result is 0 or not. And there's a C flag and a V flag, and according to the discussion that I had with your colleagues in the face-to-face lecture, you've seen those in CO and DSD, so you know what a carry is. So whenever you have an adder, for instance, you've noticed that one of the outputs is a carry, and if you're making an adder out of half adders, so you need to propagate the carry anywhere or another. Fair enough? So this means that the result that you're outputting, well, we're gonna find out if it's the exact result or it's a result with a carry that you can use. And the overflow, apparently you've seen it as well. This means that whatever you're doing, if you're using 32 bits and the result cannot be represented in 32 bits, so it feels like you're representing partially the result, and there's an overflow. So the result, the output, will not fit in the 32 bits, for instance. All right. Now the big question is, I'm gonna go back to what I've said earlier, and there's a pen. So here's my ALU. Here's my ALU, and apparently the control signal of my ALU has 4 bits, and the 4 bits are encoded in that way to know which operation is happening in the ALU. Now what I'm gonna do is I'm gonna create a control unit for my ALU. So why bother? I'm gonna have a ALU control unit for a reason, because as I said earlier in today's lecture, I have 3 types of instructions. So for each type of instruction, I will need an operation. However, I need to know what kind of operation will happen with the instruction that I'm dealing with. Fair enough? So if it's a memory instruction, I need to find out what kind of operation. So if it's an R-type ALU operation or it's a branch operation, I need to know what kind of operation should happen inside of the ALU. So I need the control unit for the ALU that will output the operation type of the ALU. So this would be the output of the control unit, which is the input of the actual ALU. And then, in order, using the instruction types, I will have an input for my control unit. Now I'm going to find out how many bits and what are the things that I need to cover here. Let's do that. So let's see. 3 types of instructions. Where's my pointer? Here's my pointer. So 3 types of instructions. Load and store. So memory instructions. So what kind of operation do I need to deal with the memory? So the memory needs a base and an offset. So in order to reach somewhere in the memory, all I need to do is to add the offset to the base. So to add, this means that I have an addition operation. We good? Do the same for a branch equal. So remember how to compare 2 variables, 2 content, two registers, to register contents. All I can do is subtract, and if the result is 0, I can go ahead and know that they are equal. So I need to subtract here, a sub. What about the R-type? Whoop, the R-type, well, it's crazy because an R-type means it's an R-type ALU operation, and it could be literally anything. It could be an AND or add, subtract, anything. So how would I do that? How would I know that? What kind of operation exactly is meant by a particular instruction, R-type instruction? Well, I can refer to the opcode. However, in MIPS, the opcode for every R-type instruction is a bunch of zeros. So how would I tell? How could I tell? Well, I'm going to use the funct field, the function field. All right. So I need systematically an add operation for any memory, systematically a sub operation for any branch, and nothing systematic here. I need to check the funct field before knowing what kind of operation is needed for the R-type. Right? So I have 3 things to take into consideration. Hold on. So 3 things to cover using binary. How many bits do I need to cover 3 things? 2 to the power of 0, no. 2 to the power of 1 is only 2. 2 to the power of 2 is 4, so 4 is bigger than 3, so we're good. So we need 2 bits to feed the ALU control unit, the one that will generate the 4-bit that is needed to know what kind of operation is needed and is done in the ALU. Right? So it's a 2-bit control unit. So let's do that. So if it's 0, 0, so this is, they decided that the 0, 0, 0 is the memory instruction, and an add is needed for any memory instruction. And remember from before, the add is 0, 0, 1, 0 as the 4 bits input to the ALU. Right? Subtract, it is that, so I need 0, 1 as a control. And finally, for the R-type, it's not systematic, so I cannot know what kind of operation before checking the funct. Fair enough? So if I have the R-type, which is coded 1, 0, could have been 1, 1, but they decided it's 1, 1, 0, right? So I'm going to go ahead and check the funct fields, and this is what I'm doing right here. So depending on the funct, I would know whether it's an add, etc. So see, an add here, I'm seeing back again the 0, 0, 0, 1, 0 from before. All right? So if someone is reading in the data path, I'm reading that I have 1, 0, I need to check the funct field, and if the funct field is a bunch of zeros, this means that I need to do an add inside of my ALU. See? So 1, 1, 0 here will lead to, in case of an add, will lead to 0, 0, 1, 0 here. So an add will happen here. if I'm having a store word, for instance, I will read 0, 0 here. This means that I have a store word in the sense of it's a memory instruction, right? So I read 0, 0 here. Systematically, I know I need an add, so the output of the ALU control unit will be 0, 0, 1, 0, and I will know that I have to make an add here. We good? Alright, so typical final exam question. I'm giving you that schematic here, and I'm telling you that there's still something missing in order to cover everything here. What is it? So for sure I'm reading the ALU operation that I'm expecting, so this is done by here. For sure I'm generating this, but there's still something missing that I haven't covered. What is it? Well, you can notice here that I still don't have the funct. So I need to feed the functs to the control unit as well. We good? Alright, so see the big picture, including the ALU up. So the ALU up will be fed the 6 bits of this funct field, and then something will decide what's going on in here, what kind of operation I'll do in the ALU. So pause the video, contemplate upon that, and this is the end of today's lecture. Have a nice one, and I really hope to see you face to face. Those who I've never seen face to face, and I keep on discovering that I haven't seen a lot of people. All right, have a nice one. Bye bye. Oh, by the way, I'm gonna deal with those later on. So the control signals, it will be for the next lecture.